I have the honor to present last speaker today, last but not the least, the very expected, Ayende Rahien. Please enjoy his speech.
I'm here to talk about my dogs. Okay, so I don't know why you're so excited, because what I'm going to talk about is these two wonderful dogs. Anyway, let's see. How many of you read this book or heard about it? Just raise your hands. So this is a very popular book. It's an economic book. It's not a science. It's not a computer science book, but it's still a very interesting book because of one assumption that it makes. People respond to incentives. That means that if I tell you that if you raise your hand, you will get $5, most of you will probably raise your hands. It's not that you really need $5, but $5 is a good incentive to raise your hands. How many of you know about this one? Anyone? Yes, please raise your hand if you know about meat and false dog. Second dog. Okay? And this is a very simple law. If something is in motion, it wants to keep in motion. If it's still, it wants to stay still. So far I showed you some animals, some economics, some physics. What is that? So now we're in Disney. So what is this all about? How many of you have used a relational database in the past? Okay, take down your hands. How many of you have not? Anyone? Okay. So I'm going to talk about NoSQL. Why do you care? I'm going to tell you about the history of the war. And the history of the war is a very simple history. By the way, which war are we talking about? The database wars from the 80s. Not the one that we are having right now. But in the 70s and in the 80s, there was a huge competition between the different databases that existed then. You have the ISO database, the structural file databases. You have this whole list that I have in some other list, in some other slide, but I don't recall the data point. We have relational database. We have RClip and DBase and all sorts of stuff like that. And by the time the 80s have started, by the time the 80s have finished, the relational database have won. And Oracle was promised 30 years hegemony over the world. And while we're visiting this question, why are we now starting to talk about non-relational database all of a sudden? And as you can see, we have all of those guys. And everyone who bet on relational database in the 80s have won. But the problem is that circumstances have changed slightly since the 80s. Okay? Yeah, so this is, I think that at some point I just started doing random pictures. This is, I think, famous pictures from the announcement of the end of World War II. And here's the question. How many of you have used a non-relational database? Okay. Which? MongoDB. Which? Okay. That's good. Someone here raised their hand? Yes. Which one? Azure Blops. Okay. So anyone who didn't use a relational database just died. Because a relational database is, a non-relational database is basically the registry, it's a cache, it's a file, everything is basically a non-relational database. And every time the app config is app settings in .NET is a non-relational database. So, given that, the major thing that we have to understand about relational versus non-relational, the core concept of relational database is that in some fashion, you store the data in the database, and then you make queries on that and get the values back. And it's the responsibility of the database engine to actually take the data that you have written to the database and get it back out again in whatever form you have done. And for the most part, SQL is actually really, really good about doing that. It's not that good about doing that efficiently, but that's another issue. So, here's the question. How much of your time can I buy for 1 GB of disk space? A year? Anyone here want to work for a year for 1 GB? A month? Okay, a day. What?
10 seconds.
10 seconds. Okay, that's actually a good number. Do you want to do the math for what it means? Because this is from a few months ago, and basically this is a 2 TB disk that goes for $70, which translates to 35, or maybe it's 35 cents per gigabyte. But you know, this is a consumer hardware. This doesn't really mean much. So let's talk about actual production stuff. And I went to Amazon and I went to Azure and priced what it means. So over a year, a gigabyte cost $1.68 or $1.8. Just for comparisons, this is about the price of a can of Coke. So now, how much time can I buy for? How much of your time can I buy for a can of Coke? Okay. Now, those are the numbers that we have right now. Okay. What were the numbers when the database war had been settled? What would be the cost of, you know what, let me ask you differently. The year is now it's 1980. And I want to go and buy a hard disk. How much space can I get? How much? 10 megabytes? 600 megabytes? 640 kilobytes. Okay, let's stick with megabytes because I cannot do translation from megabytes to kilobytes to whatever. Okay, not in my head, not in this time. So we had 10 megabytes at 1980. Anyone else want to give me some numbers? At 1980, yes. 1 megabyte. What else? 500 megabytes, okay. Just to give you some ideas, in 94, I think was the first time that you actually could buy a 500 megabyte that you wouldn't have to take a mortgage for, okay? That is 14 years afterward. So let's talk about 10 megabyte. In 1980, how much would it cost to buy a 10 megabyte hard disk? 10K? More numbers? 20K? 100? No? Take a look. So in 1980, a 10 megabyte drive was wow! And it cost $3,398. In adjusting for inflation, that's $9,000. That's $9,000 for 10 megs. Just to give you an idea, that means that what I'm going to do right now is to take a picture of the audience. So side 1, center, and the storage for those 3 pictures would cost me $9,000. Okay? 3 pictures, $9,000. Damn. Okay? And adjusting that for a gigabyte in size, that's close to 1 million. Okay? So let me ask you again. how much of your time can I buy for $1 million? Okay. Still 10 seconds? Now, that is a very interesting aspect of the numbers. Because even if you wanted to, you could not buy a gigabyte in 1980. You probably literally could not because there wasn't enough hard disk in the world. Even if you could, what would you plug this into? I mean, seriously, there isn't any machine that can take 1,000 disks or 100 disks. So let's talk about salaries. And this is a yearly salary based, again, with adjustment for inflation before taxes. So this one translates to about 3,700 per month. And that means that this is the value that we have right here. This is what you would have made in the 1980s. Continue with the numbers, that means that 1 gigabyte at the 1980s would buy me 73 years of work. Versus today, it's 5 minutes. So we are hugely expensive. Okay? So just think about that. 73 years, $1 million. That was what it would have cost us to just get 1 gigabyte. Given those numbers, does it make sense to optimize for space? No? Right in the 80s, it would have made a lot of sense because literally you could not get a bigger machine. Today, if you have a log file on a production server that is actually never getting deleted, and it grows at a rate of 1 gigabyte per month, if it's going to take you more than 5 minutes to log into it, and change the login configuration, it's not worth your time. For all practical purposes, this space has become so cheap that you really don't have to think about it that much. Okay, what else has changed? So I talked about this space. What else has changed since the 1980s? Performance. Performance of what? Okay. Processors. What? Memory processor. Everything in the hardware have jumped up. Okay. That is an interesting observation. We'll get to that later. Okay. What else? Because this is, by the way, very important. But we'll get to that later. What? Network speed. Network. Just that. Okay? Anyone remembers this UI? This was DT. This is how you write software. The master details for. Anyone remember opening a VB book and reading all about that fancy new innovation? That how you can show both the master and the details in the same page. Oh wait, it's not a page. The page is a web. This was in the same form because we're talking about Windows application. Amazing. That was considered to be really, really good UI. You probably would have won awards for that. Now, what is very interesting about this UI? How many queries does it take to load this data? 1, okay. Probably actually 2. Okay, 1 for the master and 1 for the children. Maybe you need to do a job or 2. How does today's UI look like? Anyone want to bet how many queries this takes? This is from Campfire or one of the other Basecamp or whatever. Okay, how many queries does this take to render? Easily, it could be a couple of hundreds. Okay, I hope that it isn't, but it certainly could be. How many of you ever tried to optimize a page to discover that it is generating 10,000 queries per page load. 10,000 per page load. Anyone? Am I the only one? Okay. 1,000 per page load. Okay. 500? Okay. Guys, it's so easy to get them. Anyone ever had a heavily optimized page that still takes over 30 queries to generate? Yeah? Why is that?
Different controls are separated, and we want to reuse the same functionality. And when we put the same controls on different pages, we can avoid them having multiple requests.
Okay. Let's go back here. In this case, it's very clear, one select, two select, done. In this case, the amount of information that we have to load is ridiculous. We probably have to load the same amount of information, the same information several times, just to look at it in different functions. And that means, you know what, it's not even that. Think about the amount of, just raw amount of information that we show the user. We don't show them, just here's a single item. We show them all of the items, all of the history, all of the actions, everything happens at the same time. And the user needs to see it immediately. And the user needs to see it fast. Speaking of which, 1980s, how many users? One. If you will, I'm writing a multi-user system. It has 3 users. It's complicated. Okay, today? Yeah. So think about all of those changes that were made during that time frame, and consider that the decision to use relational database has been made when you had 3 users, when this was the UI, and when that was what you stored the data on. Okay? That is a whole lot of stuff that have changed. A whole lot of stuff that is no longer relevant. But following the nothing is broken, so we don't need to fix it, we are still using relational databases. And you know what the really interesting part about this? The really interesting part is that for all of that, for the most part, relational databases actually work pretty well. Until you get into the situation where you're trying to force an inherently non-relational model into a relational database. And when that happens, that is when you start screaming, because you really have to fight the database. How if you have schemas that need to support dynamic columns, user-defined columns? How do you do that? Dynamically generated schema. Okay. Do you know what entity attribute value is? When you have a table called tables, and a table called rows, and a table called columns, and a table called values? Anyone ever had to work on one of those systems? Isn't it fun? I mean, that is how I learned that SQL Server has a limit to the number of joins that it has. Ego, open distributed transaction. Alexander, open distributed transaction. Create user OL, commit distributed transaction, we still have a problem. What are we missing? What? Login. Okay, do the login as well. You're still missing the problem. Oh, let's do replication. So Alexander, whenever you have a new user, replicate to Ego do the same, okay? So Alexander, create new user Bob.
Done. Create user. Done.
And now we're done creating the user. That's wonderful. Okay, so now creating user Bob.
Create user Bob?
No. Bob probably exists because now,
Yes, it's okay.
so now we have an exception. We have successfully fixed the problem, right? Okay. Igor, create a user John.
Create a John. Yeah. Done.
No, you cannot talk to him. He's down. So, Alexander, no, excuse me. So Igor is up, Alexander is taking a rest. I'm trying to create a new user. What's going to happen now? We have one server that is up, one server that is down. How do we deal with that? That is the CAP theorem. The CAP theorem basically says something very simple. You have consistency, availability, and partition tolerance. Choose any two. So we can have consistent and available, but not partition tolerance. What it means in practice, that if we have a consistent and available system, we can never have anyone cut the wire between the two. In the real world, this is not possible. The nearest that you can get to is a cluster server that is physically sitting on the same sun. And even that, you can have problems if someone shut down the sun. But if we live with the fact that we have partition in the network, if we live with the fact that Alexander may decide that he's getting tired of me saying jokes and just sit down, then what choice does Igor have? Igor may decide to, okay, I'm going to accept this right, and Alexander doesn't know about this right. Now we are in an inconsistent state. Or he can choose to say, you know what? I'm going to reject this right because I can't tell Alexander. And what this means in turn is that, oops, we now can no longer accept right. We are now no longer being available to the user. You see the problem? There is a probably complex there is actually a mathematical proof for this that shows that you cannot do that. I cannot follow that, but apparently there is. So coming back to Google and Facebook and the CAP theorem, relational database does not scale very well, or at all actually, because of the CAP problem. So Google and Facebook decided, okay, we need something different, and they started working with NoSQL stuff. They didn't call it NoSQL because that thing didn't exist. But eventually there was the big table, there was a bunch of other products from Google that were publicized, and then people started talking about it, and then people started creating products around this, or RavenDB, MongoDB, and all the rest. RavenDB is actually the youngest one of them. So here is the actual explanation. Okay, one of the core concepts of relational database is the notion of set theory, of the notion of working with sets. So if I don't have access to the full set, there isn't much that I can do about this. So I can access the whole set over the network. Oracle has a feature called rack that does that. It works for 3 machines. After that, it's dead. And the problem of trying to access all of the 100 machines that I have in the cluster is that you literally cannot do that. And as you suggested, the solution for that is just shard the data. What is sharding? Row partitioning, okay. I don't know what this means.
It means that you hold a set of data, a set of rows on one machine and another set of rows on another machine.
Okay. A good example for that would be, okay, all of the users starting with A are going to be in this database. All of the users starting with B are going to be in this database. Now I split the data, and now I can handle that much more users, because every database now holds only part of data. And the good thing about that is that essentially I solve the problem. The problem is that now this is no longer relational. And that means that if you want to do, okay, give me the count of all the users across all of the databases, now you have to issue n queries to all of the database, and then do the second order grouping, do the aggregation again when you get the data back from the user. That's something that you probably don't want to do. And then you know what? We don't care. I'm just going to go home now. You don't build software for 500 million users, so we don't really care, right? We are working on building a new login page. We are working on creating software for companies, and we have from five users to tens of thousands, but that's not it. 1 million users, that's it. Why do we care about NoSQL? Why are you sitting here listening to just go on and on about this? Anyone want to give a suggestion? No one. Okay. So you're forcing my hand. I have to give you all the secrets. Come on, guys. Why do you care about NoSQL if you don't care about scale? What? Development speed. Okay. Is that something? Yes. Oh, sorry, I didn't see you.
Less of an impedance mismatch, and you're forced to come up with a better model in order to make it work.
Less of an impedance mismatch, and you come up with a better model to make it work. Okay. You don't have the problem of mapping from objects to tables to rows. Not quite. It's not pure object storage, but we'll talk about this in a second. Guys, anyone ever had this conversation? Anyone? The project manager comes to you and says, I want this feature to work just like Google. And we say, okay, can I have the Google budget? No, but can you do it by tomorrow? Okay, and the answer is that you may not have to deal with 500 million users, but your users are going to expect the stuff that Google does to happen in your software as well. And it's really funny when you think about it, but some of the things that Google is doing, if you give it to users, they love you. You know what? Something as simple as suggestions. Oh, you search for that, but this doesn't exist. Let me see if I can give you something better than that. Those are features that are actually fairly easy to implement if you have the right tools. But coming back again, okay? So the data modeling, the development speed, when you don't have to fight with the database is tremendous. Just to give you some idea, let's see what the next slide is. Okay? Even if you don't need scale, okay? You don't need, to scale to 500 million users. You may still want to scale, 100,000. That is perfectly normal thing to do today. And sharding is your friend, though. But when you use relations, the sharding strategy becomes much, much harder to work with. And columns, rows, they aren't friendly. They make you take your entities and chop them into little pieces and then put them in boxes. And when you want to get them back, okay, let me take it from here and put it here and here and here and here and here and here and here. Okay, 17 joins later, we may have an entity. Or we may have run into the limit of the database. And this is a huge, huge pain. You have no idea how many times I went to a customer and, we want to use dynamic fields. Because, for example, we sell our software to different customers. Every customer wants, they have different fields that they want to store for the customer. And it's a pain to manage, it's a pain to query, it's a pain to report on. So, and then we have this. This is the huge problem. Please read this. So, how do I query the database? It's not a database, it's a key value store. Okay, it's not a database. How do I query it? You write a distributed MapReduce function in Erlang. Did you just tell me to go and pimp myself? I believe I did, Bob. And that particular thing is the reason why people are scared of NoSQL. Because it's freaking hard. You have to write distributed MapReduce function in Erlang. Anyone wants to do that? No. I mean, anyone wants to do it for fun? Maybe. Anyone wants to do it because their job depends on that? Okay, so that is a huge problem, because what people remember is very early projects that did things in that way and were very hard to use. And what we actually need to support is the sort of tools that we actually need, sort of things that we actually want. So let's talk about this for a second, okay? How much time do I have? I have no idea what.
30 minutes.
30 minutes, okay, that's wonderful. So let's talk about it for a second. I want to build something. Can someone give me a model? Anyone? Give me a model to build. Yeah, give me an example of something that we want to build. What? Oh, come on. Just because I've been to prison for 3 years, that doesn't mean that it has to follow me around. Yes, what do you say? Yeah, yes. So, okay, let's talk about a problem with doing a prison system is that I cannot make it simple. Okay, I have to do all the details because otherwise, let's do a blog post. Okay, I'm sorry, it's simple, but if you want to do the prison system, go with the blog. So anyway, we have the notion of a blog post and we want to put it in a database. And as it turns out, this is actually very simple to do. We create a blog post, we save it into a database, and it's stored, at least right now I'm going to talk about how RavenDB does that. Okay, there are other ways of doing that, but let's talk about this. And then we just store that as a JSON document inside the database. So that's fine, that's okay. But what are the next steps that we want to do in that? Once we have stored the data in the database, we need to query it. Okay? And this is where we actually run into a problem. Why do we run into a problem when we want to query that? How is the database, notice what we didn't do. We want to store a blog post in the database. If this was a relational database, what would have been our first step? Create a table. Create a table to put the data in. With RavenDB, we didn't need to create a table, we just put the data in. So, most NoSQL solutions are schemaless. That is actually an interesting statement. Why are they schemaless? Why do we even have a schema, do you know? No. Why do we have a schema in relational databases? You need what? Because you have columns. The actual reason for that is that the definition of the schema defines the format of the data on the disk, and that is how it's used to make queries on the values. There's also a bunch of set theory math that we don't really care, relational algebra, but the basic idea is that all of the items in the set must share the same schema. And now we get into different, so in relational database we have a schema, we have to create that, and we have to adhere to that. What if we try to write to a relational database something that doesn't match the schema? We get an exception. But think about the use cases for doing something like that in a NoSQL system. Anyone ever had to upgrade the schema of a live database? Anyone ever failed doing that? Okay. So think about what happens, again, thinking about the scaling solution, if you have 50 databases that you need to update the schema on. Anyone wants to do that? Anyone? You're scaring me. So anyway, so we don't have schema in most NoSQL databases because we don't really need that. We don't have sets, so the data doesn't really have to be the same. And if we had a schema, That means that we need to update it across the entire team all at once. That is freakishly expensive. It also means that from a development perspective, I can just start writing code and store it in the database, and now it just works. So we store stuff into the database. What is the next step? To query it. How do I query something in a database? There are two options. What? No. Think about the modes. We have the first option is to query it by the primary key. And querying by primary key is actually very, very easy. Because regardless of how the information is stored, you have some sort of primary key that you use to store it in the actual disk. So if you want to query by the primary key, it's like that. Do the lookup on the actual storage format, get the value back, send it to the user. How useful is being able to query by the primary key? What?
Table has cluster index.
Okay, yeah, so basically we are querying on the primary cluster index, yes. But what happened if that was the only thing that you had? Would it be workable? If you could only query a database by the primary key, is this the same way of doing business? How many of you, a database that you can only use a primary key for is for a table storage? In a table storage, you have the partition key and the row key, if I remember correctly, and that is the only thing that you can query on with reasonable performance. If you try to query on anything else, well, go away for a month, maybe we'll give you a result. With RavenDB, if you want to query by the document key, which is the primary key, it's very easy for us to give you a result. But it turns out that while it is possible to make queries, to make an application to only use the primary key, it's not really a good idea. So what other options do we have? We have to create some sort of indexes. This is something that actually is quite important. You never make a query in production without an index. Why is that? Because it's considered unacceptable to shut down the server for a single user. Because if you try to make an unindexed query, what does the server have to do? It has to do a table scan. It has to load all of the data, check that value, and against the predicate that you have specified. That is hugely expensive, especially when you're talking about, oh, we have more than a single row in a single document row, or however the data is stored in the database. So you always have to have indexes. But, okay, so we always have to have indexes, otherwise we get in table scan is ON, N is very, very big, and O is pretty expensive as well. Okay, what's the next step? So we want to define some sort of an index. We define an index. How does it run? Right now, by the way, I'm not talking about using multiple databases or multiple servers, just one server, one database on it. So we define some sort of an index, and then we make a query on that, and now everything is good. How do we define indexes? How do you define index on schemaless data? What? Schemaless data, yes. So I can put any data whatsoever. No. So we have data with no schema. So I can put one document that has name, user ID, and email, and a second document that has email address, full name, and user ID in the different system is 5. Okay? There is nothing whatsoever that limits what sort of fields I can put in the database. So how do I make queries on that? Any suggestions? What? Can you raise your voice? I'm sorry, I can't hear you.
You just query whatever you want.
Okay, you can just query whatever you want. And the secret here is, even though you don't actually have a schema in the sense that the database enforces that, most of your documents most of your data is going to follow some sort of a common shape. I'm not using the word schema intentionally. For example, I may want to query all of the documents of type post that has the author ID 5. So what I'm actually doing is making two queries. Give me all the documents where type equal to post and author ID equal to 5. And here's an interesting question. When do we define these indexes and how do we define them? Different databases treat this differently. With MongoDB, with CouchDB, for example, you have to write a JavaScript function that would extract the type and the author ID from the documents and write it to an index, and then you go and query that index. This is CouchDB. With MongoDB, you can make an unindexed query, but this runs in memory, and it's an ON operation. So we always write indexes, but let's leave that MongoDB aside. All of the indexes in Mongo runs in memory, and I think this is an insane decision. With RavenDB, you have two options. You can either write an inquiry that would output the fields that you want to index, and then you can make queries on that index. Or you can just say something like, you know what, let's just query the database. What would happen then if you just say, give me all the documents with no preparation whatsoever. Give me all the documents that type is post and the author ID is 5. Anyone?
Index is created.
Okay, so there are actually three things that we could do. One of them would be, you know what? I don't have an index that answers this query. So I'm going to reject this query. I'm going to say you have to create that index up front. And from a logical perspective, this is the right thing to do. From the guy who has to make sure that the database is always on and operating in the best, in the highest capacity. If you haven't defined an index, you cannot make a query. The problem with that is that this makes development really, really hard. So the other option would be, you know what, okay, I will just do a table scan and scan the entire database for the documents that matches your values. The problem with that is that people will use that and go with that to production. And suddenly you have an unindexed query that is hugely expensive, and the more the system grows, the slower the system becomes. With RavenDB, what we have done is something a bit more complicated. When you give me a query, we have the query optimizer that runs and figures out if there is an existing index that can match this query. If there isn't an index that matches this query, we aren't going to reject the query. We're going to create an index for you. Now, this is a temporary index that exists only in memory. But the more that you use this index, the more that you make queries that hit this index, the more important it becomes. At some point, we are going to say, you know what? I think I like this index. I'm going to keep it around forever. Because that index has been promoted from a dynamic index to a static index. They are going to be maintained by the system throughout the life of the system. Because apparently you really care about the result of this index. The second part that we have here is what we're actually, just think about the implication of doing that. You build a system and you make queries on that, and based on the behavior of your application, the database is going to optimize itself to work for your application. This is a feature that wasn't written by me. I was actually fairly insistent that it's not possible to write it. And a guy called Rob Ashton had a discussion with me on the mailing list, and he says, oh, I think we can do dynamic queries, and I think it would be fairly simple to do, and blah, blah, blah. And I said, no, it cannot be done. Sorry, you're wrong. And he says, no, I'm pretty sure that you can do that. And eventually I gave him my standard answer. Okay, show me the code. And I was absolutely certain, you have to be absolutely certain that I will never hear from that guy again. And he comes back tomorrow with, okay, here's the code. This is how it works. I'm like, this is, by the way, one of the most important features that we have right now. Because this is, I think, a really, really awesome feature, because it means that you can make life so much easier. You don't have to worry about stuff. Not that you have to create the index, and not that the performance will be stored in production. It just works. Okay, so we have different types of NoSQL databases. We have the document database. What is a document database? A document, it's not a PDF or a Word document or stuff like that. This is an XML or a JSON document. Usually the format is JSON. Then we have the notion of a graph database. Graph database is usually used to make queries on graph theories, graph work stuff. What do you mean? For example, I want to ask the question, what are the friends of your friends? Or what is the shortest path from me to Greg? Okay? So for instance, in this case, it's 1, 2, 3, 4, 2, all the way to him. This is mostly used for social networks and stuff like that. Then we have key value store. Key value store, think about this like a dictionary, but distributed. Then we have the notion of a column family store. Column family store is Bigtable, Cassandra, HBase, all of those. And those are this is actually fairly complicated to explain, but think about the relational database. Now, take the table and transpose it 90 degrees. Instead of looking, and instead of the most important thing being the rows, the most important thing in column family databases is the column. And you cannot make a query using anything except the primary key. What this means is that you manually, you know what, I have a blog post specifically about this that experiment with code samples and some visualization. It's fairly hard to talk about this right now. Just the most important thing about this, you take a relational database, you remove the relational, you still have rows and columns, but the way that you work with that is drastically different. It took a long time for me to actually figure out how to think about this properly, and I'm still probably not very good at it. So here are a bunch of relational databases, non-relational databases. This, and this are document databases. Trinity and Neo4j are graph databases. Cassandra and HBase are column family databases. Okay? And the most important thing that you will notice with them is that they tend to be very, very fast. Why is that? Why are they fast? What? Optimize for it, okay. What's more? No joins. The most important thing about them is that for the vast majority of cases, we can make a query very, very efficient. Given that, usually by the primary key, usually by a prepared index. For the most part, we do very little computation during reads for all of those. This is a different trade-off from having to do a lot of computation on the read, but very little computation on the write, which is what most relational databases, are doing. Trade-off means that we also model the data differently. We tend to have bigger data points. So a document in RavenDB, for example, would contain data from multiple tables in a relational database, because that data can be treated as a single item. At no point do we need the entire data set. We don't need to ask questions over the entire thing at once. Or if we do it as a batch process that gives us the result in a different table, instead of having to store all of the items at once. Okay, this is important. The disadvantages of NoSQL is that usually the data is built to be used in a certain way. If you want to, in a relational database, if you have a data and you want to start writing queries against that, you can actually get you can actually write a lot of queries and get a lot of data out of the same shape fairly easily, because that's the huge strength of relational database, the dynamic queries ability that it has. It's also the biggest weakness because the problem with performance. With NoSQL databases, usually we fit the data structure to the task at hand. And if you want to answer different questions, at some time we will have to restructure the data to be able to answer that. In most cases, this is actually what we want, in the same sense that we have a reporting database and RavenDB database, then we want to have different databases to fit the question that we actually want to answer them, because then we can tailor each database, each solution, directly to what we want, instead of trying to have, you know, the best, the least bad option for all of them. And we don't generally do add queries. And again, this is basically the same set of decisions that we make when we want to run on RDBMS in real production systems. And this is for RavenDB. Okay, safe by default is interesting one. What does it mean, safe by default? Anyone ever crashed the system because they had an unbounded query? Just select star from table, and suddenly the table had 100,000 items in it? Okay. Anyone ever, again, made a query to the database in a loop, and now we have hundreds of queries per page? Yeah. Okay. I'm watching you. Anyway, so one of the, okay, so I've been doing databases, I think, since, I've been doing database commercially since 2014, and I've been called to a lot of places to solve a lot of problems regarding how people use databases, specifically with environment. When we started working on RavenDB, one of the design decisions that I made was, I do not want to have the same problems. So with RavenDB, if you make too many queries, then we'll actually throw an exception that says, I'm sorry, you're making too many queries, you're doing it wrong. You can configure that away if you want, but we will not let you, if you try to shoot your feet, we'll actually tell you, are you really, really certain? And only then we will actually blow your head off. Okay? Doesn't really mean shoot your feet, blow your head, that's better. So a lot of the problems that you usually have, but you know, it's not that the developer or bad, it's just, oh, right now focus on the user experience. I'm not actually worried about optimizing the data access stuff. But you never actually get to optimize the data access stuff, and then it goes to production and things break. So that's why we are actually very careful about making sure that you got into production, you didn't optimize stuff, things will not fall over and die. We'll either put a break immediately, or we'll throw exception when you try doing too much. We actually have a couple of really interesting cases where we have Stack Overflow questions about, oh, we just hit that exception. And the message for this exception is like that. This is what happened, this is why it happened, this is how we fix it. And about 10 minutes after that question was posted, we have in a comment to that question, oh, I figured out what happened, I need to move the query outside of the for each loop. And I consider that a huge success for that feature. Then we have the self-optimizing and zero admin. We talked about it, how, oh, you make queries, this is more important than that, so we make this into a permanent index. The more that you query a particular index, the more efficient it becomes and stuff like that. And we have something called eventual consistency in RavenDB. This relates to reads and writes. So in RavenDB, reads are really, really cheap, and writes are also very, very cheap. But at some point, you actually have to write the indexes. And with RavenDB, we do that in a background thread. That allows us to do a whole bunch of optimization. But what it means is that a millisecond after you wrote a document to RavenDB, if you make a query on that document, and that query is not a primary key, you may get a stale result. That is part of the way that RavenDB is designed, and the benefit of that is that it's able to give you really good speed for a whole lot of scenarios. And if you really care, oh, this query shouldn't get still resolved, you can ask for that and you get that. Then we have the ability to extend that and simple API, and it's really, really fast, which I like. No. Anyone know what this is? For a long time, I ran my blog Subtext, which is a really, really nice blog engine. And at some point, I decided to move to RavenDB, so I rewrote a blog engine in RavenDB. And this is the number of queries that it took to render the main page. So this is the home page of the blog, and it takes 11 queries. Just to give you some idea, this is the number of tables that it had to touch. Quick, how many tables does it touch? No. Notice that the number of items that it touched several times. Okay? And this is, look, this is not, this is something that I want to emphasize very carefully. This is not a bad code. This is not a bad project. I was running that for years and years. It's an excellent project. It's hand optimized, store procedure, blah, 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 blah. All of the best practices stuff. But the problem is that because of the modeling in the SQL database, we really had no other, they really had no other choice but to go in that direction. And that means that you have to query 19 tables to show the main page for my blog. So we decided to go in a different approach. And here is a document. Okay, this is a post. You can see some very interesting things here. You can see that we have an array directly inside that post. It doesn't have to be in a different document or different table or stuff like that. Documents can be arbitrarily complex. Now we have an array that contains a complex object and stuff like that. Just this, just the different modeling means that rendering the home page for my blog now take 5 queries. Okay? And you can actually see what's going on. Okay? This is a query. Give me all the posts that hasn't been deleted and have been posted, and their publish date is up to a certain point in time. Give me the blog config and give me all the section. That's the stuff that you see on the right side of the blog. Give me the statistic, give me the archive. It's fairly simple. Okay? And that's all you need. And here is some code. So here is us querying RavenDB. Again, this is a dynamic query. So you can see that we query that. We query a nested property inside an array. And here's how we load stuff. Okay? Some interesting things. And now we have 5 more minutes, so this is the time for questions. Can you give him the mic? Thank you. Last slide, yes.
How to refactor documents? Okay, for example, when you have a property inside the document, if you want now to make a collection of this property.
You just do it.
No, I mean you have a bunch of old documents.
Okay, so you have all documents and you want to take a property and make it into a collection, and you don't want to lose the data that is over there. You write a migration script that basically pull it out and do it that way. It's fairly easy to do. So it's maybe 5 minutes work to do something like that, just run over a bit and do that. It's the same sense that you would write an update statement in a migration stuff. This is actually one of the most complicated migration steps that you have. If you want to add a property, if you want to remove a property, it just happens. You don't have to do anything to do that. More questions? I think there's some more of them. Yeah.
Go back for one slide.
Yes.
One more. And one more.
Yes.
Don't stop.
This one?
Go ahead.
Yeah.
We have a bunch of queries here.
Mm-hmm.
But I'm sure most of queries could be cached with, for example, in case of Hibernate, we could use second level caching. And also we could use output caching in EES or something else. So you could have a situation when no query will be run against database.
Let me put it in very simple terms. The query cache that you're talking about is really nice, except that let's say that we are going to cache comments. The moment that we insert any new comment, all of the cache for all of the queries, for all of the comments have become stale and have been dropped from the cache. Notice that what we're talking about here is actually pre-cache, pre anything whatsoever. Both in this example and in the RavenDB one. What happened actually with RavenDB is that the client API already does caching for you because of the way that we structure things. We can do that safely without worrying about stale results from the server. So yeah, you could do caching. It's not trivial to do so. I usually, when I'm doing the Hibernate course, I'm usually spending about 2 hours just talking about the caching and what it means and what sort of problems do we have to worry about when we use them within Hibernate. So caching is not a silver bullet in this case. Okay?
Thank you.
You're welcome. Yeah.
I have one more question. Can you just scroll further? Next
Go
slide.
back.
Next slide. Yeah, okay.
Yes.
So as far as you can see, you have here blocks and posts, and data here is duplicated, so it's quite optimized for reading. But for instance, I
don't see duplicate data here.
For instance, I would like maybe to save tags for Ayende. So just imagine, I would like to see all the tags from Ayende, and then I can have a situation where we have both tags on users and posts. What if I will update my current post about Raven? And
so you're talking about what happened if I denormalize the data and now I have to update it?
Yes. So I know that you have special update indexes, but also I know that it's not actually quite a good idea, at least you say.
No. So what happened if I wanted to have, let's say that I wanted to have a list of all of the tags by OM on all of the posts, right? I wouldn't duplicate the data here. I would create an index that would answer that question for it. For the most part, denormalization is usually useful for 2 reasons. One, if you're actually working in a sharded environment where reaching out to the different values may mean hitting the different servers, because we have the notion of live projections and include that gives you the values from different documents. Think about it like doing a join without all of the problems of joining. That is one option. And the other option is, one is that use denormalization if you have multiple servers. The other reason is if you explicitly want the data to not change if the raw data have changed. For example, in an order line, you keep the price of the product as it was when you created the order line, not when it is now. Okay? Because you want to track whatever you have changed or not. So the answer is that for the most part, you don't denormalize more in a document database than you would in a relational database. And if you do, then we have ways of solving it. It's not ideal, but it works.
Okay, so what if I would like to change my model? I would like to modify posts or create a next entity. So how can I update all my current existing?
You have 2 options. One of them is we have the ability to patch existing entities and the ability to do it across all of the entities that match a specific query. Think about it very similar to an update statement that you can write over everything that matches specific queries, or you can say, okay, I'm going to do the code and just pull everything and load it back again. For the most part, it depends on how flexible you want to be. It's fairly easy and it's take minutes to do. Either way. More questions? I think, yeah.
What if, for example, if you store the comments to the blog post and you have a commenter's name on it, and then you have a separate document collection about this, people who are posting comments, and you want some extra property, for example, property is this commenter is really annoying, and then in the next version you have a requirement to show on a comment from this annoying person, show maybe some red star or something. Then you have to query two document collections, and basically you are querying the database in a for each loop.
Yes.
So how you handle it the correct way.
Okay. A good example, let's say that, let's talk about this model. So when I want to show this page, I also want to show the title of the blog, the name of the blog. So one option would be to load this post and then load the post blog. That would be two queries. And obviously if we have a collection, that would be n queries. But with RavenDB, we have the ability to tell the server, look, I want a document that is pointed to by this property. We call it include. So load post 349931, include the document pointed to by the blog property. And at that point, it will give you this one and that one as a single request to the server. This also works for nested values and for collections. So you're able to say things like, okay, give me all of the commenters that are listed in the comments collection dot commenter ID, whatever, something like that, and that will give you everything in a single result. And then you can just get it back and move on.
So like a join.
Not like a join. Because no, the reason that it's not like a join, it doesn't happen for the entire data set. It's happening only for the page that you're getting back, and you don't have to worry about things like Cartesian product. For example, if you have 6 comments from a single user, that user document will only be returned to you once. You don't have to worry about all of those things. And because this is efficient in that way, it means that you don't have to worry about, oh, I have to have a multiple collection that I'm including from, and suddenly my query becomes too big. More questions? Over there, Kim.
What about transactions between two documents? Can I update two different documents in a single transaction?
With RavenDB, yes. Okay, just to expand on that, one of the problems that some people have with NoSQL is that they have to give up transactions. I like transactions. In fact, in my blog, I have a blog post that says something like, you will pry transaction from my cold dead hands. And this is regard to MongoDB's inability to do transaction. With RavenDB, you have the transaction of a single document in the sense that this is ACID. Either the document will go to the database and will be saved there, or the update will be totally cancelled. You can have that over multiple documents as well. Again, fully ACID in the sense that it's all there or none at all. You can have that between multiple servers. So that is basically doing a DTC commit, a system transaction commit. I strongly recommend against that because of the problem with DTC, but this is something that works and works very well. And it just works, and transactions are there, and I'm very happy because it makes sense, you know? It doesn't make sense to me to have a database with no transactions. More questions? Going once? Going twice? I think we have one? No? Yes. Am I still working on Hibernate? My company still offers commercial support for that. My company still develops a profiler for Hibernate. We're actually working on that actively. I'm not that involved in the Hibernate on a personal level anymore, no. More questions? What? Randomox, same thing. The guys who are mostly doing stuff with Randomox right now are Tim Banks and Stephen B. Holland. I'm sorry, I cannot pronounce his last name. And they are the guys who are mostly taking care of that, answering many questions in the mailing list and doing things with updating the source code and stuff like that. More questions? Oh, yeah.
Thank you. Is it optimized for the return parts of the document if I have Ajax queries and want second page of comments?
So you're talking about what happens if I want to load just part of the document? Yeah. So you can do that. You can just say, okay, I want to fetch me just part of the data. For the stuff that you said, oh, I want to take that part of the comments out, this is probably something that would be handled in an index and page into an index, not through doing it that way. But yeah, you can do that. And yeah.
Okay, to what your queries materialize to?
Can you just raise your voice?
To what queries are materialized to? What is behind the scenes?
Behind the scenes with RavenDB, we take your queries, we translate them into a link query, and then we execute that link query against your documents, and we take the output of the link query and put it in a Lucene index. If you're still following me so far, what this means is that the thing that we query is actually a Lucene.NET index. That means that you have support for doing things like full text search, comparison, ranges, spatial queries. We even have the ability to do things like, oh, you made a query, but there are no results for that. You probably need that one. And we can give suggestions about what the user has made when they ask for something. So that's it. And yes.
Do you support aggregate like sum and count, like functions, aggregate cycles?
So how do we handle aggregates over multiple documents? And the answer that for doing that, you have to write a MapReduce index. You don't have to do that in Erlang. But the way that you do that is you write two link queries. That's basically it. One of them that specify what is the data that you want to get, and the second one that specify how to do the aggregation of the query. The reason that we need to make this into two queries is that we split the execution of the index into separate parts, and that allows us to optimize the way that we actually query that. And I think we had another question over there. No? Okay.
As far as I know, you use receiving for indexing. I'm wrong. Yeah. So, and as far as I understand, indexing is created dynamically. And how do you decide what type of indexing is in what analyzer and what other things?
So I don't want to get too deeply into that. If you want to talk to me, that I'll be happy to. But basically, we have two types of indexes. We have the ability to do dynamic indexes, in which case we are setting the defaults, and that basically means, oh, you're going to match an exact match. We don't do full text search or those sort of things, but we have a lot of smarts going on. So, or you index over a property or an in property, so make this into an in field and stuff like that. The analyzer is lowercase analyzer, but we don't do full text search on that. And that's what, if you want to define a static index, this is when we give you all of the power of Lucene. Yeah, you can configure analyzer, you can configure sort, index, all of those things. More questions? Yeah?
Can we say that RavenDB allows to use single storage for CPU arrays?
You could say that, but I think that Greg will try to kill me. Okay, so you could say, we actually have an example showing how you could store the commands as documents in RavenDB and have an index that processes them and output the view data, the read store into the index. This is certainly something that people are doing. I'm not sure if this was what was the author intent when you're talking about that. But certainly it is the case that we have people that are storing data into RavenDB and using indexes. They sort of mix it up and change it into different shapes, and then just read directly from the index all of the values that they want. Another common thing to do is basically to treat the RavenDB as the persistent view store, because you can have arbitrarily complex data there, and because it's very, very simple for us to query that very efficiently. So we have some sort of command store, and the view store is actually RavenDB because you load, update, and modify that. And then when you read from that, you just read the whole index, usually with a primary key, and that is all the information that you need to render a single page. More questions? Yes?
Can you tell us about pricing model? How can I try it? Because it's commercial product, so.
So, by the way, Kirill, how much time do you have? Or am I overrunning? Minus 10 minutes, okay. So that would probably be the last question. Okay, so the model for RavenDB is that it is open source and commercial both at the same time. That means that if you want to use it for an open source project, you just can. If you want to develop with it, even for a commercial project, you don't need the license to do that. If you want to go to staging, production, stuff like that, this is when you need to buy a license. Okay, and it's like, I think it's $25 a month or $600 for lifetime versions and stuff like that. Okay, guys, if you want to ask me more questions, I'm going to be here, and I'm probably going to be here even after the panel, whatever. So feel free, and thank you very much.